Let's get started again. I hope you enjoyed your lunch. So the next speaker is, again, a guest speaker from Oxford and DeepMind, EYT, speaking on Distill and Transfer Learning for robust multitask reinforcement learning.
Thanks, Sebastian. So this is joint work with a bunch of people at DeepMind, and it was just presented at NIPS, just the past NIPS. So I'll start with a bit of an introduction to reinforcement learning. So we have an agent. The agent is trying to act in an environment, and the environment is sending observations to the agent, and there's some rewards that the agent gets. And what the agent would like to do is to maximize its reward by acting in this environment. Okay. The way people typically formalize reinforcement learning is using what's called Markov decision processes. So we have agents, and so we have the actions of the agents and the states of the environments over multiple time steps. So we have S is going to be states of the environment, A is going to be actions of the agent, and this is for time step 1, and then we have time step 2, time step 3, and so forth. Okay. And we're going to call that the trajectory over state and action pairs, and we're going to denote that by tau. Okay. So, and the way Markov decision processes work is that we're going to assume the following. We're going to assume that that we have some transition dynamics. So basically, given that the environment's at some states S and the agent takes an action A, what's the distribution over next states in the environment? And we're going to assume that this is Markov. And what that means is that given the current state, the future state is independent of past states. Okay, so basically, the current state captures all the information about the world. So that's the environment dynamics. We also have rewards that the agent receives. So we think of this as just a function that basically is high if the agent gets a high reward if it takes that action in that state. Okay, so that's the reward. And finally, the last ingredient here is the policy that the agent, okay, and this is the thing that we want to learn. And we're going to assume that the policy is going to be basically a distribution over actions that the agent can take in that state S. Okay. So this together defines a joint distribution over these trajectories, right? And the problem of reinforcement learning is basically to find policies that maximizes this expected reward here. Okay, so we have a sum over time of the rewards at each time, and we're going to assume that there's some sort of discount factor gamma between 0 and 1, which basically discounts future rewards. Okay, so basically we get the agent to pay more attention to rewards that is going to arrive closer in more in the more what's the word in the recent not too far away. Okay, so so if you're going to receive a reward long time from now, you're not going to worry about it basically. Okay. Right, and this is an expectation over basically the environment dynamics and the policy that the agent takes. Okay. So that's a reinforcement learning, and what we're interested in here is multitask reinforcement learning, and basically what I'm going to make that to mean is basically that we have a set of tasks indexed by I. And basically, for every task, we have a different transition dynamics, a different reward function, and we're going to learn a different stochastic policy as well. And basically, this is the thing that we want to maximize for each task I. Okay, so you can see here that I'm basically going to. So, of course, these are multiple different tasks, but at the same time, we want them to share some similarity, right? And I'm already assuming in here that the state space of the environment and the action space of the agents are the same across different tasks. Okay, so imagine that you have different tasks. So in the experiments later, I'll show some experiments where the agent is basically like a first-person shooter sort of game, right? It's a three-dimensional visual environment. We're going to assume that the state consists of this three-dimensional visual observations, and the actions that the agent can take will be like move forward, move backward, turn left, turn right, and so forth, and shoot and stuff, and jump. Okay. So basically, the state space, we're going to assume that the state space and the action space are the same across these different tasks. Okay. Okay, so, and of course we're going to assume more than that, because what we'd like to do is to say, well, if we have multiple tasks and they're all related to each other in some way, we should be able to learn them faster if we learn them jointly as opposed to learning them separately. Okay. And the idea that we have for this distill and transfer learning is the following. So we're going to assume that there are separate policies for each task. And we're going to also assume that there's going to be some centroid policy, okay, or you can think of it as a prior policy. And this policy is going to serve as a communication channel between the tasks. And one way in which you could think about this is that each pi I here is going to be a policy that we're going to learn to act well in this task, while pi naught in the middle here is going to be a policy that the agent would take if it doesn't know which task it's in. Okay, so it's kind of like almost like a default sort of behavior if it doesn't know which task it's trying to solve. Okay. And it turns out that so we're going to formalize an objective that I think makes a lot of sense for something which looks of this form. And interestingly, the algorithm that we end up deriving has quite interesting behavior, which is the following. So basically, this centroid policy is going to be learned via a distillation process from each of the individual task-specific policies. And that's going to learn some sort of common behavior across the different tasks. And the way this pi naught is going to affect the individual task-specific policies is via regularization. Okay. Okay. Which is, I guess, why we call this distill and transfer learning. So we're kind of distilling towards this central policy, and then that's going to allow us to transfer knowledge or transfer behavior across the different tasks. An intuition that maybe you could have is, imagine that in one of the tasks, the agent has learned that if it sees a corridor that's quite long, that it should just walk down the corridor as opposed to dithering along the corridor. Then that behavior could be useful on other tasks as well, which may have corridors. So if agent 1, so if pi 1 learns that behavior, then that gets distilled into pi naught. And then that behavior is now going to, basically what that's going to do is it's going to encourage the other agents that maybe hasn't learned that behavior to reproduce that behavior. Okay, so what's the objective that we use? Basically, the way we're going to do this, so I think I've used this trick a few times across my career, but basically we're going to take a hierarchical Bayesian approach. Okay, so we have the task-specific policies pi I, right? And this bit here is the average reward that we would like to maximize for task I. And what we're going to do is to say we're going to introduce a KL a penalty term, which says that by default, we're going to prefer that the task-specific policies are similar in a KL sense to this default behavior, to this default policy. Okay. So this bit here is the KL. So if you take the expectation over pi I into here, you just see that that's a KL between pi I and pi naught. But it's not the usual one in that there's a discount factor here as well. Okay. Right. Okay. So and that's basically the setup. Maybe I should have made sure. Oh, I've got the time. Okay. So and okay. So if you think about now optimizing this joint objective over all the different tasks and over this default policy, then there's kind of two things that you want to optimize. One is the default policy and one are the task-specific policy. So I'll go through each of those in turn. Okay. So if you think about learning the default policy, fixing the task-specific policies, then you see that the only term that the default policy depends on is this log pi naught term, right? And if you try to optimize this, basically that's just a supervised learning problem. It's just a maximum likelihood sort of behavior. So basically what the default policy will try to learn is if pi I has high probability for an action, then pi naught is also going to learn to give high probability to the same action in the same state. Okay. So this is basically just distillation. Okay. And this is something that people have explored in the past. So there's a work by Rousseau et al. And Parisotto et al. That they call policy distillation or policy mimic. The difference from these two works is that in these two works, it's kind of the learning is a two-stage procedure where in the first stage we learn the task-specific policies independently. And once that's learned, then there's a distillation process that learns pi naught, and then that's it. Well, what we're doing here is actually once we've learned pi naught, that in itself also is used to regularize the pi i's towards pi naught as well. Okay, so it's kind of an iterative procedure. So for those of you who are familiar with reinforcement learning, you can see that this objective here is actually very similar to a lot of the recent KL or entropy-based policy regularization techniques, which people use to make sure that the policy that the agents learn don't prematurely converge to some suboptimal behavior. Okay, so it's basically used as a way to regularize so that the agent can explore properly in the space. But it turns out that actually learning pi naught actually breaks its use as a regularizer for exploration, because typically in these applications, pi naught is just a uniform distribution over actions. And basically what that's saying is that if you haven't learned what to do in that particular state, then you should just try all the actions. Okay. But if instead pi naught has actually itself learns that it gives high probability to one of the actions and low probability to the rest of the actions, then that's going to discourage exploration. Okay. So basically, actually what we did is very simple. We're going to have the original reward average reward term. We're going to have this KL regularization, which implements this distillation and transfer process that shares information across the different tasks. And in addition, we're going to have an additional entropy regularization term that encourages the agents to explore further. Okay. Okay. So in the following, I'm going to, so of course there's hyperparameters, C, KL, and C entropy. And I'm going to rewrite this in, basically reparameterize it using two different parameters, alpha and beta here. Okay. Just to make the math simpler later. Okay. Okay. So, so I said that, so I've described how the learning for pi naught works. I haven't really described how the learning for the pi i's work. There's actually been a lot of work in the literature now that has explored this idea that of kind of doing entropy regularized reinforcement learning. And there's very interesting connections between that work and actually probabilistic inference. Okay, so if you go back to this equation here, and if you're familiar with variational inference and you squint a bit, you can see that actually pi I here, you could think of it as a variational posterior distribution. This term here is basically the log likelihood that you want to maximize. And this term here is basically a KL between the prior and the posterior. Okay? And basically this is just a variational objective, and it corresponds to that. And people have made that connection before. And you can actually solve for the optimal variational posterior distribution in that context that we have here. And in our case, what we get is the following. Is that what we find is that the optimal pi I given pi naught is going to be of a form or given by the following. So basically, it's going to be pi naught raised to the alpha times another term here, which is e to the some advantage function raised to the beta. Okay. And basically, you can think of this as a prior and think of that as the likelihood. And this pi I just computes the posterior distribution. Okay. I have an equality term here because the normalization term is actually kind of rolled into this advantage function. It turns out that the advantage function here is, you can think of this as the value of taking action A in state S relative to the value of the state S. And it turns out that this value of the state S actually serves as the log normalization constant in this equation. Okay. And these are all softened in the sense that we are kind of softening it by adding this additional entropy regularization or KL regularization. Okay. So this is also quite interesting from the perspective of how do we parameterize our policies. In particular, how do we parameterize our central policy and how do we parameterize the task-specific policies? Okay. So in deep reinforcement learning, it's very sensible to say, well, let's use, it's not very, it's typical to say that we're going to parameterize our policies using neural networks. So given a state S, we're going to learn a neural network that gives us a distribution over actions if the agent finds itself in that state. Okay. And similarly, we might say that, well, we can also parameterize the advantage functions using neural networks as well. Basically, we have a neural network that will compute the advantage of action A if the agent finds itself in state S. Okay. And basically what this kind of optimal form tells us is that the optimal form for pi I, for the task-specific policies, should have this following structure. Basically, given some observations or given some observations of the states of the environment, we're going to have a neural network that computes the default policy, and we're going to have a separate neural network that computes the advantages, and we're just going to basically do a weighted sum of these two things in the log space, and then exponentiate and basically passing it through a softmax, and that's going to give us our optimal form for the task-specific policies for task I in this case. Okay. This notation here is a bit of a cross between neural networks and graphical models. We have a plate over this neural network for each task, basically. Okay. So we basically replicate that with different parameters. Okay. And basically, that's how we parameterize. That's how we propose to parameterize the task-specific policies. And this is actually quite interesting because if you start off by looking at this a network architecture, we could say, well, let's just learn our stochastic policies using standard reinforcement learning techniques like policy gradients or active critic methods. And we parameterize our task-specific policies using this sort of network architecture. But let's not worry about this additional KL regularization between the pi i's and the pi naughts. Okay. If you do something like this, you could imagine that there's some form of non-identifiability between basically between these two columns of the network. Okay. And the addition of this KL regularization between the pi i's and the pi naughts, basically what it does is that it forces this column here to learn everything that it can learn across all the different tasks. And so what this column actually is forced to do is to learn like the delta between this default policy behavior and anything that makes it work on that particular task. Okay. So it kind of removes some of the non-identifiability and it actually makes the learning more stable that way. Okay. So I'll just skip through this. Basically, we've compared 4 different variants of our algorithm with the standard at the time, which is a asynchronous advantage actor critic methods, A3C methods. And I'm just going to skip through to some of the results. Basically, it works pretty well. So this is an example where basically the solid lines are the different variants of our method. And the two that actually we kind of end up proposing is basically the actually the red method and the green method. And they basically the reward that it gets is it learns pretty fast and it gets to kind of better policies in the end. Okay. This little example on a Great Wall task is quite interesting because what it shows is that what the default policy learns is quite interesting. So this is a case where we have 2 kind of rooms, 2 parts of the space, and we have a long, narrow corridor that connects the 2 parts. And the different tasks are basically just getting the agent to get to a different position in this environment. Okay. So these are 4 different tasks here, where the green is just the goal state. Okay. And the agent has to move from anywhere in the space to the goal, basically. And you can see that what the default policy has learned is the following, is that if the agent finds itself in this part of the space, and if it finds that it is going down this corridor, then it should keep on walking down the corridor in the same direction. And if it finds that it's moving right along the corridor, then it has learned to keep on moving right along the corridor as well, which kind of makes sense in this context. So from the perspective of hierarchical RL, basically this looks like learning an option without really it looking like an option. It's kind of interesting, I think. Okay, and this works on kind of more complex domains as well. Anyway, so what we've proposed here is kind of a faster and more robust algorithm for multitask reinforcement learning. And basically what this does is that it assumes that tasks have the same physics. And so they are solved by policies with similar structure, and that similar structure is captured by this default behavior that we're learning alongside each of the tasks' specific behaviors. Thank you.
Time for questions.
So a different way of doing this sort of hierarchical multitask RL would be to sort of assume, when you say that the tasks have the same physics, the way I would interpret that is that the dynamics of the tasks is the same.
Yes.
But here there is no representation of the model explicitly. So the
no.
P
Yeah.
of S prime given S A. Any thoughts on that? I mean, do you think, because averaging across policies, you could get it to fail?
Yeah,
right?
yeah, it's true. Yes, yes. So I think that there's lots of different ways in which one could think about transfer across different tasks, because different sets of tasks are similar in different ways. And I think that would be another way in which we could have kind of commonality across different tasks and transfer across the tasks. And this is kind of one way. I'm not saying that this is the best way. It's just one way, I guess. Yeah.
Maybe one more question, and Matt.